So two amazing guys, big, broad grins on their faces because they have too much fun applying the highest of high-tech to the lowest of low-tech human power. Welcome, guys.
Thank you. Thank you very much. I'm Todd. This is Cameron. This is us here. And as you can see, we build flying bicycles. Cam and I have actually been working together for the last 8 years on a variety of unusually awesome projects. Everything we work on runs entirely on human power. So to put that into context, that's effectively the power of a cordless drill or a motor that's small enough to fit in the palm of your hand. Yet on this tiny, tiny amount of power, we're able to reach highway speeds and we're able to achieve human flight. Really all of this, it's about doing more with less, about using the power of the human mind and body to make the impossible possible. To us, really it's the most impossible challenges are the most interesting because they force us to really think differently. They force us to think of new and creative ways of tackling problems. So we got our start in 2006 on the human-powered ornithopter project. The goal of this project was to achieve an ancient aeronautical dream, to fly like a bird, no engine, no propeller, just simply flapping our wings. This has been a dream that's been around for hundreds, if not thousands of years, from ancient Greek mythology to the sketches of Leonardo da Vinci. And when we first got introduced to this, sort of got dragged into this by a professor that we like to call Dr. D. He's the cool one with the sunglasses there. He was our professor in doing our master's and PhD. And his lab had been working on trying to understand the mysteries of flapping wing flight for the last 20 years, really trying to understand what birds are doing. They had succeeded in flying the world's first radio-controlled flapping wing aircraft, the world's first hovering flapping wing aircraft, and it even worked on some full-scale piloted aircraft. But the idea, being part of this lab, it was hard not to wonder if this original aeronautical dream of human-powered flight or human-powered flapping wing flight was really possible. But at the time, the current belief was that it in fact was not. And the argument goes like this. This is what we call the Great Flight Diagram. Basically, if you plot everything that flies, from insects to birds to bats to full-scale commercial aircraft, everything falls along the same curve if you plot the flight velocity versus mass. The problem is that as you go up this curve, if you're heavier, you have to fly faster. And flying faster takes a lot more power. The power required to fly is going up faster than the power available from the muscle mass, and eventually you reach a limit where it's physically impossible to fly on a metabolic engine. It's physically impossible to fly using muscles and breathing air if you're more than 25 pounds. And that's where the line stops. That's where there's no birds basically bigger than about 25 pounds. So how do we get past this physical impossibility? Well, the thing here is, the cool part, if we're going to call something impossible, we have to look at, what are the constraints? What were the assumptions that went into this model? And the assumption here is that we're following this curve. But this is simply a trend line, and we don't have to follow the curve. For their mass, a human-powered aircraft flies incredibly, incredibly slowly, thereby taking a very small amount of power and making it possible for a small, weak, feeble human to take to the skies. So the really cool thing here is that this is not about, some new age technology. This isn't about computers or materials. This is just about a different way of thinking.
The first person to think really differently and get off this curve was Paul MacCready, who in 1979 created this aircraft, the Gossamer Albatross, that flew across the English Channel. He was able to get this aircraft so slow by making it incredibly light and incredibly large. We knew from this that the human-powered aircraft problem was possible, but flapping wing human-powered aircraft was definitely going to be a step up. Armed with, again, looks like 80% of the problem is solved. We know it's possible. We moved up to a barn north of Toronto in Tottenham, a group of students ready with our theoretical knowledge to start attacking this problem. But in true student fashion, we hadn't actually accumulated the hands-on experience yet required to build this human-powered aircraft. So again, we did what students do, and we went on an epic road trip. We went to see every single human-powered aircraft in North America to really figure out what made these things tick. Fortunately, this only took us 3 days. There are not that many human-powered aircraft around. But by the end of this trip, we knew how to make these things work. And when we finally designed and built the Snowbird, it looked like many of these other aircraft, which meant substantially different than any aircraft that you have ever seen. It had a wingspan of 105 feet, but weighed only 95 pounds. It also did not have a propeller. Instead, in the yellow fuselage you see there, the pilot, sitting in the cockpit, does a leg press, and that leg press flaps the wings down to drive it forward. We designed an ultra-long, ultra-flexible wing to very precisely twist as was required to produce the forward thrust in order to drive the airplane through the air. With all of the engineering behind it, though, we end up with an airplane that is kind of awkward to handle, requires a farm tractor for assembly, and wants to blow away at the slightest hint of wind. So we end up testing with all of our best friends at 5:30 in the morning. It's a great excuse to hang out before the crack of dawn. Fantastically enough, what you end up with is an aircraft that you can still actually run alongside. And after 4 years of research, we finally were able, in 2010, to make this aircraft the realization of our goal and this ancient aeronautical dream. So almost as inspiring as seeing that thing fly along the runway was the realization that this was a lot of fun. We as students were having a great time doing what we were doing and realized that this was not only something that combined all of our interests, but had a great impact on youth and the public. We were getting letters from kindergarten children who'd been inspired. And we really were looking for a creative outlet to do a lot more of this. And we found that in the Atlas Human-Powered Helicopter Project. In 1980, the American Helicopter Society had created the Sikorsky Prize, calling for a human-powered helicopter to fly for 1 minute and briefly reach an altitude of 3 meters. However, in the 30 years this prize had been around, it was older than either of us, no one had come close. In fact, in that whole time, there had only been 3 helicopters out of 36 attempts that had even gotten off the ground, and then for only inches of height and seconds of duration. Now, we had a lot to learn from these other teams, but we realized that this was a great call for some out-of-the-box thinking. For one thing, all of these teams had designed their aircraft to fly inside the nearest, most convenient gym. We decided to first build Atlas as big as necessary and then figure out where to fly it. It turned out it was twice as big as anything that had ever been built before. And initially, when we were talking with Moses about maybe bringing it here to display in the auditorium, we wish we'd had this chart. It is as big as most commercial aircraft. Again, though, it weighs only 120 pounds, substantially less than the human pilot.
So this thing is absolutely massive, and as Cam said, we're trying to find somewhere to fly this. We were lucky enough to find a full-size indoor soccer field that we could test this at. But this scale, I mean, we knew this was going to be a highly flexible aircraft. It was going to be very difficult to manage, and that new scale drove all aspects of the design. So the rotor itself, if you look at it, it looks much more like an optimized wind turbine blade than something you would typically see on a helicopter. This comes from computational optimization methods. The structure below is a wire brace structure. Basically, this is the structure that holds all of those big rotors together. And it is just a spider web of wires everywhere. But it turns this structure into a highly efficient arch. And it makes it so that for a very, very small amount of weight, we can actually have a structure that is somewhat stiff. If you zoom into that structure, again, another spider web of high high stiffness lines. Anything that is in compression is a carbon fiber tube. It's not quite carbon nanotubes yet, but at least carbon fiber tubes. And then we have Vectran lines holding it all together. The drive system is actually really interesting. It works like a reel-to-reel tape. I don't know if anyone still remembers the old tapes, but basically you have a spool around the rotor, and when you pedal the bike, you're unspooling line from the rotor and you're spooling it up onto the bike. So you only have about a minute and a half of line, which was all that we needed for the prize. The prize required 60 seconds of flight. So it's a very lightweight, very elegant solution specifically for this prize. I suppose as long as your commute is no longer than about a minute and a half, it's a great commuter vehicle. The control system is something that was really, really interesting. It started out as this massive, complex sort of Rube Goldberg machine that we were very proud of, but in the end, absolutely didn't work. It was about 30% of our design time, construction time, and flight testing time that we literally just had to rip out. But it was an understanding how this failed. Basically, the structure was just too flexible to make this work. So we tried to use the flexibility of the structure to our advantage. And by tying 4 small lines from each of the hubs to the bottom of the bike, what happens is when the pilot leans, it actually pulls on those lines and it bends the entire structure. The whole thing just flexes, it tilts the rotors in the direction that you want to go, and that's how we control it. And this is something, honestly, there's no way we could have figured this out from the outset. This was just by seeing it fly, seeing it fail, seeing how flexible it was, that we could come up with something like this. So the construction actually went reasonably smoothly. We had moved back up to that same barn with a small team of students, and we built the aircraft in only about 3 months. But when it got to flight testing, of course, things were a tad bit more difficult than we had anticipated. Every day involved painstaking, tiny, almost microscopic adjustments to the angle of the rotors to get the angle just right so it wouldn't drift, or the rotors wouldn't go out of balance and crash into the ground. This big spider web of lines, everything had to be finely tuned and adjusted. So hundreds of lines that you're trying to adjust the tension of to get this thing tuned. And eventually, when you got around to trying a few flights, at best we would get in maybe 8 flights in a given day. Then, of course, it's 6 o'clock and the soccer players want to come in and we have to pack this thing up. And, rain or shine, or we had a few snowstorms, basically we would pack this thing up into a 52-foot trailer ready to get out there and do it again the next day. So that was on a good day. On a bad day, we would break things. And we broke a lot of things on this project. We really, through progressively bigger failures, began to understand how much failure is a part of success. And there was twice that we were literally inches away from the prize when the whole thing came down. So that actually pretty much happened twice, about a month back to back. But we definitely, that stopped. Could we maybe just skip to the midway through that video? Or we can watch it again. Everyone wants to see it crash again, right? This is the best part of the presentation. Just keep this rolling. Can we just put this on loop until the end of the presentation? Wait for it. But at this point, we knew we were close. I mean, twice we were literally inches away. We knew that it was physically possible. But most importantly, we had an unbelievable team on this, an absolutely passionate team that all had signed on basically without the promise of pay. And we're just on board to try to do something that had never been done. So on June 13th, we climbed on board and tried one more time for the Sikorsky Prize.
So as exciting as that is, through these past several years, the fastest things that we've worked on have been these speed bikes. And they are a recumbent aerodynamic bicycle in this optimized shell, capable of highway speeds on human power alone. And this is another area in which people have been very quick to say things are impossible. And so in 1992, this team, the Cheetah, went 68 miles per hour, or 110 kilometers per hour. And they thought that they had reached the limit and that nobody would go faster in the next, 100 years. They had fancy engineering degrees, and they had a professional cyclist, and they thought that they had reached the limit. But lo and behold, just a few years later, along comes a Bulgarian sculptor and a Canadian athlete, recreational athlete, and they took that record from 68 miles per hour to 83 miles per hour in just a few years. And that may not actually seem, despite the that I heard here, like a huge increase, but because aerodynamic power scales with the cube of speed, that represents a bike that is twice as efficient as what seemed like the pinnacle of design. Every year now, a whole community comes together from all over the world in Battle Mountain, Nevada, and everyone is trying to get the biggest speeding ticket and push the boundaries of efficient and lightweight engineering design. The greatest part of this whole competition is that the limit is not actually in sight. The blue line that you can see at the bottom for this 1 hour distance record has been about stagnant for the past 100 years. But the green line is for these unconstrained speed bikes. And you can see that it's actually still going like a rocket with no end in sight. So with this bike here, last year we were able to achieve 78 miles per hour, about 125 kilometers per hour. But we know that we can go faster. This bike has been designed, and we will be working with further advancements in aerodynamic shape optimization, low rolling resistance tires, and even, no canopy, camera vision technology. We're in the middle of this project right now, and our goal in September is to break the human-powered land speed record. We're deep into the design with our new student team on this bike you see here, which we've named ADA for its pursuit of ultimate efficiency. We're in the middle of our Kickstarter campaign, we're prototyping, and things are starting to move really fast now. We're even planning for our next project, which in 2015 will be an airplane designed to fly a marathon in 1 hour. This is another thing that we've been told is impossible. Our whole goal with these projects is to inspire people to think differently about big challenges and really show the public and youth that those big challenges are really worth taking on and that impossible is only temporary. Thanks very much. Thank you very much.
Thank you. Thanks, guys. I was really disappointed when they told me they couldn't bring the helicopter. Did you collect the $250,000 for the Sikorsky Prize?
We did.
You did.
Yes.
Bravo. That's fabulous. That's fabulous. Last question, how do you get into that? Do you like...
It's not easy. The biggest improvement actually on the next bike is that you can get into it a lot easier. The shell comes off here and you sneak in through the back. It's a little bit of a tight fit and definitely takes some practice.
Now, who's the pilot?
On these vehicles, the whole team gets to ride. I've been the primary athlete on it, but we like to give everyone a shot.
And what's going to make the difference between this one and the next iteration?
It's going to be, again, pushing the technology a lot further than we've ever done before. So the next bike will be even smaller. The aerodynamic shape will be even better for high speeds. We'll have even better tires for lower drag. And the drivetrain, for example, the mechanicals will be much more efficient than ever before. So really looking for efficiencies and looking for improvements in every single aspect of the design.
Hopefully the pilot will be a little bit stronger too.
All right, well, you'll come back and celebrate that next record with us. Inspiring.
Absolutely.
Thank you.
Thanks very much.
Thanks.
We're going to do a photo, guys. Yep.